Okay, so okay, I hope the screen is visible. So welcome back to the 11th TA session on the NPTEL course Principles of Signals and Systems offered by Professor Aditya Jagannatham. So my name is Yashvanth and I'm presently a PhD student at IISc Bangalore and advised by Professor Chandramurthy. And my research interests lie in signal processing and wireless communication systems with specific research focused on intelligent reflecting surfaces for beyond wireless communications. So you can contact me at this email for any queries that you may have, and also look at this particular web link to know more about me. So today the topic that we are going to discuss will be on discrete Fourier transforms. Okay, so as usual, the first part of today's session will be on summarizing week 11's lecture. Okay, so broadly, week 11, the lectures of week 11 dealt with solving problems related to discrete Fourier series or discrete time Fourier transform or discrete Fourier transform. Okay, so basically, several example questions were being solved by the professor. And so recall that in the last session, we had discussed properties and we solved problems on DTFT, while the last of the previous session we discussed problems on discrete Fourier series. So we are going to focus today's session on discussing properties, theory, and problems related to discrete Fourier transform. So discrete Fourier transforms are basically meant to be defined for a finite length sequences x of n. So basically, you define discrete Fourier transform as follows. So x of k, where k represents a frequency domain variable, defined as sum over n equal to 0 to capital N minus 1. It's a small mistake. X of n into e raised to minus j 2 pi k by capital K n. Okay, and this k, the index at which we compute the discrete Fourier transform, also varies from 0 to capital N minus 1. So note that your time domain signal x of n is also varying from 0 to n minus 1. Similarly, the frequency domain the discrete Fourier transform also varies from 0 to n minus 1. Okay, that is both the time domain x of n and the frequency domain x of k have n samples in total. So here, this number e raised to minus j 2 pi by capital K, 2 pi by, okay, this is capital N. Okay, 2 pi by capital N is what is called as a twiddle factor in the literature. Okay, the representation is capital Wn. So once we have taken the Fourier transform to define a signal x of n in its frequency domain, a natural question would be to ask, okay, so given the the Fourier transform, how do we recover back my time domain signal x of n? So essentially, the answer to that lies in the inverse discrete Fourier transform, where basically you do the expression is very similar to that of your Fourier transform, except that now instead of x of n, you have x of k, and the summation is over all the frequency domain variables small k. So this e power so basically the exponential argument remains the same except for a change in sign, right? So there was already a negative sign, now it has become a positive sign. And then you have a 1 over n scaling, which is not present in the Fourier transform. The reason for the 1 over scaling is to preserve the energy between the time domain and the frequency domain. Okay, so in terms of twiddle factor, you can write the definition for inverse discrete Fourier transform as 1 over n x of k. This number is equal to w power minus km. That's because wn is defined as e power minus j 2 pi by n. So if you want to define e power plus j 2 pi by capital N times small k times small m, that you have to take a negative sign here, so it becomes w power w subscript n power minus km. Okay, so that is basically the expression for inverse discrete Fourier transform. So as I told you, both x of n and x of k will have same number of capital N samples. Okay, and now having studied discrete Fourier series, discrete time Fourier transform, all for a discrete time signals, a natural question then is, okay, how do you relate discrete Fourier transform coefficients, that is these x of k's? How do you relate this x of k's to the discrete Fourier series coefficients and discrete time Fourier transform coefficients? Okay, so the relation between discrete Fourier series and discrete Fourier transform is given as follows. So recall that discrete Fourier series was constructed for a periodic discrete time signal. So if I consider a periodic version of your x of n, then what happens is the corresponding discrete Fourier for coefficient at the kth frequency bin times the n, which is the n is a, for example, here it becomes the number of time domain samples in a period will be equal to the Fourier discrete Fourier transform coefficient x of k, where k is the same frequency bin at which you are computing the discrete Fourier series coefficient. Okay, this is a relation between the discrete Fourier series coefficient and discrete Fourier transform coefficient for any signal x of n. Now, similarly, the relation between discrete time Fourier transform and discrete Fourier transform is that discrete Fourier transform is exactly equal to DFT evaluated at your frequency omega equal to 2 pi k by capital N. So essentially, if I take a discrete time Fourier transform, which is a continuous representation of your signal in the frequency domain, and I sample that signal, the resultant signal, the resultant spectrum or the resultant waveform in the frequency domain is called the discrete Fourier transform. The sampled version of DTFT will give you the DFT. Okay, so now similar to how we had seen the properties of several Fourier transforms till now, several transforms. So discrete Fourier transform also has its own properties. And the properties are again very similar to the other properties of other transforms. So again, I'm pulling out this table from the reference Oppenheim discrete time signal processing, table number 8.2. Okay, so let's say you have x of n, which is a finite length n sequence in time domain, and let's say its frequency domain DFT is endpoint DFT of length n x of k. Then what happens? And let's say there's x1 of n whose DFT is x1 of k, and x2 of n whose DFT on frequency k is x2 of k. When the first property is the third bulletin is basically says this is called the linearity property. That is, if I have a times x1 of n plus b times x2 of n, the corresponding DFT is nothing but a times x1 of k plus b times x2 of k. Okay, now basically now, property 4 says that if I construct a time domain signal using the frequency, the DFT of a signal x, small x of n, then its corresponding Fourier frequency DFT will be n times small x of minus k modulus n. Okay, mod n. So basically, if you recall, professor had discussed this in the class, and this is precisely what is called the duality property of the DFT. Property of DFT. Can anyone confirm if I'm audible and if my screen is visible? Can you type or maybe can you unmute and talk? Just confirm if I'm audible or visible. Okay, I hope everything is fine. Okay, let me continue. Okay, so that is basically about the duality property. And the next property is basically time shifting property in the time domain. Okay, so basically x of n minus m modulo capital N, its corresponding Fourier free DFT will be a phase shifted version of your actual Fourier transform x of k. Here, this wn k power m is nothing but e power j 2 pi by capital N into km. Okay, that the twiddle factor power km. That is basically your this is nothing but your time shifting property. The next sixth bulletin is nothing but your frequency shifting. That is, if you frequency, I mean, if you modulate a time domain signal using a phase shifter, then its corresponding frequency domain will shift by as the same amount L, but modulo N. Uh, when is the number of samples? This is called the frequency shifting property. And seventh property, what is this? This is nothing but summation over m equal to 0 to n minus 1 x of m x2 of m minus n minus m modulo n. Its corresponding DFT will be product of x1 x2. This is nothing but the convolution property of your DFT. DFT. Similarly, eighth property, what it says, if you multiply two time domain signals, its corresponding frequency domain will undergo a circular convolution. So this is nothing but the multiplication property. Okay. Now ninth one, what it says is, if you do x conjugate of n, its corresponding frequency domain representation will be, you conjugate x conjugate, also time reverse by a factor of minor, time reverse it, but do take modulo n. Okay. So basically this is nothing but the conjugation property. And the rest of properties also you can similarly go through. It is similar to what we have seen for other transforms. Okay. And one more transform, one more property is basically the Parseval's relation that says that the energy in the time domain signal is equal to 1 by n scaling times the energy in the frequency domain signal. So this is basically called the Parseval's relation. Okay. So what this is, the physical significance of Parseval relation is that it says energy in time domain is equal to energy in frequency domain. Okay, that is basically your Parseval's relation. Okay. And 19th I wrote, but this is really the duality property which I discussed above. So this property, okay, this property is what is called duality. The 0.4 is what is called the duality property, which I've already discussed. Okay, and then basically professor had also discussed about something called the DFT matrix, which is basically used to a matrix vector relation that can convert a time domain signal vector directly into a frequency domain signal vector by virtue of something called the DFT matrix, which enjoys special properties like it is Hermitian, symmetric, and also it enjoys properties like um, your H Hermitian, H is equal to identity equal to H Hermitian. So these are some properties of the discrete Fourier transform matrices. These are some properties. Okay, so that was the summarization about DFT. Are there any questions or doubts till now? Are there any doubts? Okay, so I don't hear any doubts. Okay, so let's continue with the tutorials. The first question is, okay, thanks for replying. The first question is, let x of n be the time domain signal given as sine pi n by 2. Then let's say there's another discrete time signal like h of n equal to -1, 2, -3, 4. Okay. That means if I put an arrow mark here, that says that this -1 is correspond to h of 0 equal to -1. That is the meaning for the arrow mark. These are the two signals. Then the question is, perform circular convolution of x of n and h of n. Okay, that is the first question. So let's solve this solution. So first of all, we need to find what sine x of n is. Okay, so basically, okay, so I should also mention for n equal to 0, 1, 2, 3. Okay, so basically this is defined only for n equal to 0, 1, 2, 3. Okay, only for four samples, I'm defining this sinusoidal signal. So what is x of n? First, let's denote what is x of n. X of n is nothing but sine 0, sorry. Then at n equal to 1, it becomes sine pi by 2. At n equal to 2, it becomes sine pi. At n equal to 3, it becomes sine 3 pi by 2. And this is basically nothing but 0. Sine pi by 2 is basically 1. and sine pi is basically again 0, and sine 3 pi by 2 is basically -1. Okay, so that is basically your sine of pi n by 2. And you have h of n is nothing, I'm just rewriting, h of n is nothing but -1, 2, -3, and 4. Now, what is the expression for circular convolution? Circular convolution thing, but y of n is essentially defined as summation over m equal to 0 to n minus 1 x of m into h of n minus m, but modulo n. Okay, this is a notation. This is nothing but summation m equal to 0 to n minus. What is n here? N is nothing but 4, because we are only considering 4 samples. So it is 3. So n minus 1 is basically 3 into x of m, and this is nothing but h times n minus m mod 4. Okay. So this is nothing but x of 0 into h of n mod 4 plus x of 1 into h of n minus 1 mod 4. I'm just expanding this in terms of this summation. Excuse me. Yeah, thanks. So then plus x of 2 into h of n minus 2 mod 4. Excuse me. Plus x of 3 into h of n minus 3 mod 4. Or basically y of n. Okay. So basically then what we need to do, we need to evaluate for n equal to 0 first. So your y of 0 will be nothing but x of 0 into h of 0 mod 4. What is that? Okay, let's first finish. But x of 1 into h of 1 minus 1 is, sorry, this is, okay, 0 minus 1 is -1. So it is -1 mod 4 plus x of 2 into h of 0 minus 2 is -2 mod 4 plus x of 3 into h of -3 mod 4. Okay, so what is 0 mod 4? Yes, can you please tell what is 0 mod 4? The remainder when you divide 0 by 4. That is nothing but h of 0 itself. Okay, 0 itself. Plus x of 1 into. What is -1 mod 4? Remember, -1 mod 4 is same as -1 plus 4 mod 4. Because negative number, first we need to convert to positive number. And this is nothing but 3 mod 4. And this is nothing but 3. That is basically 4. If you put 3, ones are, sorry. Oh, sorry. Yeah. Oh, sorry. It's the other way, right? 3 mod 4. So what do you have? 0, 0. Remainder is 3. So that is basically equal to 3. Okay, so 3 mod 4 is equal to 3. Therefore, this value, which value? -1 mod 4, that is -1 mod 4 is equal to 3. Okay, so that is nothing but x of 1 into h of 3 plus x of 2 into h of what? Okay, similarly, -2 mod 4 equal to -2 plus 4 mod 4, which is equal to 2 mod 4, which is equal to 2. H of, therefore, it becomes h of 2. And finally, plus x of 3 into h of, what is -3 mod 4? -3 mod 4 equal to -3 plus 4 mod 4 equal to 4 minus 1 is 1 mod 4 equal to 1. Therefore, it is a h of 1. Okay, so we now found the expression for n equal to 0 something, but y of 0 is equal to x of 0 into h of 0 plus x of 1 into h of 3 plus x of 2 into h of 2 plus x of 3 into h of 1. So now let's compute. What is x of 0? You see here. Okay, let us write. So x of 0 is nothing but 0. H of 3 is nothing but minus 3. Oh, sorry, it's h of 0 into x of 0 into h of 0. Therefore, x of 0 is 0, h of 0 is minus 1, so 0 into minus 1 is 0. So equal to 0 plus. Next term is what? X of 1 into h of 3. X of 1, sorry, x of 1 into h of 3. Okay, this 3. 0, 1, 2, 3. X of 1 into h of 3. That is 1 into 4, which is equal to 4. Plus. Now, x of 2 into h of 2. X of 2 into h of 2. What is x of 2? X of 2 into h of 2. That is 0 into minus 3, which is equal to 0. Next, x of 3 into h of 1. X of 3 into h of 1. That is x of 3 into h of 1. Minus 1 into 2, that is equal to minus 2. So that is equal to 2. 4 minus 2 is equal to 2. Therefore, y of 0 equal to 2. Similarly, you need to compute the above for y of 1. So you can show that your y of 1 will be do the same thing as above. Okay. Basically, go back here. This is a general expression for y of 1. Put n equal to 1 here, n equal to 1, n equal to 1, n equal to 1, n equal to 1. Then what you get, I'm going to write down here. So y of 1 will be x of 0 into h of 1 plus x of 1 into h of 0 plus x of 2 into. So basically, what did we do? 1 mod 4 is basically 1. 1 minus 0 mod 4 is basically 0. Okay, so then 1 minus 2 will be equal to minus 1 mod 4, but minus 1 mod 4 is nothing but 3. This becomes x of 2 into h of 3 plus x of 3 into h of 4. Sorry, 2. Why 2? Because if you put n equal to 1 here, 1 minus 3 is minus 2. Minus 2 mod 4 is basically 2. That's why h of 2. Okay, so then just substitute for the values. Okay, what is x of 0? X of 0 is nothing but okay, 0. Okay, so now what are we looking? X of 0 into h of 1. So x of 0 into h of 1. 0 into 2, which is basically equal to 0. Now, what are we looking? X of 1 into h of 0. X of 1 into h of 0. 1 into minus 1 is nothing but minus 1. Now, x of 2 into h of 3. X of 2 into h of 3. 0 into 4 is basically 0. Now, x of 3 into h of 2. X of 3 into h of 2. Minus 1 into minus 3 is plus 3. Equal to 3. Therefore, y of 1 equal to 3. Now, similarly, what is y of 2? We need to compute for how many y? It's asked for there are n equal to 0, 1, 2, 3. Therefore, y of n will also be from n equal to 0, 1, 2, 3. We have computed 0 and 1, 2 and 3 will compute. So y of 2. What is y of 2? If you go back here, just put n equal to here. So 2 mod 4 is basically h of 2. X of 0 into h of 2. Okay, and then you can show that I'm just writing down directly. You can show that this will come out to be x of 1 into h of 1 plus x of 2 into h of 0 plus x of 3 into h of 3. Okay. So again, the x of 0 into h of 2. What is x of 0 into h of 2? X of 0 into h of 2. 0 into minus 3 is 0. 0 plus x of 1 into h of 1. X of 1 into h of 1. That is 1 into 2 is basically 2. Next is x of 2 into h of 0. X of 2 into h of 0. 0 into minus 1 is basically 0. And finally, x of 3 into h of 3. X of 3 into h of 3. 4 into minus 1 is minus 4. So this is nothing but 2 minus 4, which is equal to minus 2. Finally, your y of 3 will be nothing but you can show that x of 0 into h of 3 plus x of 0 into 1 into h of 2 plus x of 2 into h of 1 plus x of 3 into h of 0. So just find out x of 0 into h of 3. Go back, x of 0 into h of 3. 0 into 4 is 0. Plus x of 1 into h of 2. X of 1 into x of 2. 1 into minus 3 is minus 3. Next, x of 2 into h of 1. X of 2 into h of 1. 2 into 0 is basically 0. And finally, x of 3 into h of 0. X of 3 into x of 3 into h of 0. Minus 1 into minus 1 is plus 1, which is equal to minus 2. Therefore, your circular convolution is nothing but y of n is nothing but, what is y of 0? 2. Y of 1 is 3. 2, 3, minus 2, and minus 2. With arrow marker 2 means y of 0 equal to 2. So this is the answer for circular convolution. Is this clear? Yes. Is it clear? Okay, very good. So now it looks very laborious, right? So there's a lot of steps that we are doing just to find the circular convolution. See, it's so much of steps. So what I'm going to do is I'm going to give you a very nice, simple, short trick. In fact, okay, short or easy evaluation of circular convolution. Oh, sorry, not yeah, correct. Easy evaluation of circular convolution between two n-length sequences x of n and h of n. That is basically, let's say y of n is equal to x of n circular convolution h of n. Okay, let's say that this is the thing. Then can you find y of n directly? Okay, I'm going to give you, I'm going to give you a matrix vector representation, y of 0, y of 1, and so on till y of n minus 1 equal to, populate the first column with the equal to a h vector, h0, h1, and so on till hn minus 1. Okay, this is basically the same symbols, the values of your signal h stacked as one column of this matrix. I'm going to fill up. Okay. Now, the second column of this matrix is going to be nothing but shift all these guys by one length down. That is, h of 0 will come to second position, h of 1 will come to third position, so on, and h of n minus 1 will go to top. Okay, so that will become h of n minus 1, h of 0, h of 1, and so on till, so whatever was there here, h of n minus 2, okay, that will come as the last position in the second column, h of n minus 2. Let me just make one thing. Okay. Okay, so basically, if you may want me to say, this h of 0 has gone here, h of 1 has gone here, and h of n minus 2 has gone here, and h of n minus 1 has gone up. Now, similarly, do the same thing for the second column also. Okay, so what you get? So, and then the last element, n minus 2 will go up. What do you get? You get n minus 2, h of n minus 1, h of 0, and so on till h of n minus 3. That is, here n minus 3 would have been there. So what actually happened is this has gone here, this has gone here, this has gone here, this has gone here, and this has gone up. Similarly, fill all the columns until you get the following. Until you get h of 1, h of 2, until h of n minus 1, and h of 0. So this is basically an n by n matrix. This is an n by 1 vector and times another vector, that is into x of 0, x of 1, and so on till x of n minus 1. Okay, so basically all that you need to do is you are given two n-length sequences x of n, h of n. Find this matrix, basically substitute for each value with the values in h of n, and this is a vector x with h of n. Just multiply this matrix and vector. Whatever vector you get as output, each entry will correspond to the circular convolution value for 0, first instance, second instance, third instance, so on till n minus 1 instance. So at one shot, you get the values for the entire sequence y of n. Okay, so this is a short trick. So for example, here if you see one by one we calculated. We first calculated y of 0, then we calculated y of 1, then y of 2, then y of 3. One by one we did. But here, the same at a stretch, basically you can compute all the values y, all the values of y of n sequence. Okay, please ask me if there's any doubt in this construction. Okay, but yeah, this is what it is. Okay, let's move on. So basically what I would suggest is you verify the above problem. Okay, so here you have you have x is equal to this value and h is equal to this sequence. Use now n equal to 4. Use this matrix vector relation and verify that whatever y vector you get, it matches with this sequence. Just verify it once in your own time. Okay, we'll then now solve the second question. Let x of n be equal to 4, 5, 4, 5, 4, 5, 4, 5. Okay. The question is simple. Find DFT of x of n. Okay. So what we are going to do, we are just going to apply the formula for your discrete Fourier transform, namely that your x of k will be equal to, what is the expression? Summation n equal to 0 to capital N minus 1 x of n into e power minus j2 j2 pi by n k into n. And now basically this is now what you will do, basically that here what is your n is nothing but how many values? 1, 2, 3, 4, 5, 6, 7, 8. So it's an 8 length sequence. Therefore your capital N is nothing but 8. So your x of k is going to be summation n equal to 0 to n minus 1. 8 minus 1 is 7. X of n into e power minus j2 pi by 8 kn. Okay. And now basically okay, so basically what are we going to do now? And k ranges from 0 to 7. N minus 1 is basically 7. So now just substitute the values. So how many 4s do you have? 1, 2, 3, 4. It's nothing but 4 into e power. Okay, let's do one by one. 2 pi by. So what is 2 pi by 8 is nothing but pi by 4. Okay. So and now you're having what? So this is for k equal to 0. You have x of n equal to 4, and this guy will become 1 because e power 0 is 1. So it's just 4. Next term is nothing but 5 into e power minus j pi by 4n. Next term is nothing but 4 into e power minus j 2 pi by 4n. And next term is 5 into e power minus j 3 pi by 4n. Next, plus 4 into e power minus j 4 pi by 4n. Next, 5 into e power minus j 5 pi by 4n. Okay, so we have to go till 7. So 2 more terms. Plus 4 into e power minus j 6 pi by 4n. And this is nothing but plus 5 into e power minus j 7 pi by 4n. Okay, now what do we have? Basically, if you look at this, what is e power minus 5 pi by 4n is nothing but e power 2 pi minus 2 pi minus 1 by 4, is it? No. Okay, so you should write it as pi plus pi by 4. Correct? It's pi plus pi by 4 is 5 pi by 4. This is nothing but minus 5 pi by 4. Okay. You can write e power minus j 5 pi by 4n as e power minus j pi into e power minus j pi by 4n, which is nothing but e power minus j pi is what? Cos pi minus j sin pi, which is minus 1. So this is what minus e power minus j pi by 4n. Okay. And basically, if you look at similarly, what is this uh, 3 pi by 4n? Similarly, e power minus j 3 pi by 4n. What is this? This is nothing but e power j pi minus j pi by 4n. Sorry, it should be other. Okay. So basically, what is this then? This is nothing but minus e power j pi by 4n. Then similarly, what is left out? Okay, we'll see e power minus j 7 pi by 4n is nothing but e power minus j 2 pi plus j pi by 4n. Okay, but e power minus j 2 pi is nothing but cos 2 pi minus j sin 2 pi. Cos 2 pi is 1, sin 2 pi is 0, so this thing but equal to j pi by 4n. Okay, then what else is left? So basically, this is pi by 4n. This is nothing but j pi by 2n. This is nothing but j pi by 4n. This is j pi n. Pi by 4 is nothing but j minus j pi by 4n. This is nothing but, okay, 3 pi by 2n. And this is 7 pi by 4 is nothing but j pi by 4n. So let's only compute e power minus 6 pi by 4n. It's nothing but e power minus j 2 pi plus j 2 pi by 4n. Okay, that is nothing but minus 8 plus 2 is nothing but minus 6. This is nothing but e power plus j pi by 2n. Okay, therefore, using all these in equation 1. using these in equation 1. What do we get? We get x of k equal to 4 will remain as 4 plus minus j pi by 4n, that is already 1, and there is another minus j pi by 4n, and that is coming from 5 pi by 4. So this guy will combine with this guy, because this e power minus j pi by 4n is coming twice, but it is coming in negative now. So then this will cancel out. 5 minus 5 e power minus j pi by 4n. So what we took off this 4, we have finished this, we have finished this. Now what is left? This is nothing but e power j pi by 2n, and similarly we have e power plus j pi by 2n. So let's just collect them out, and this is coming for e power, and this is coming for e power minus j 6 pi by 4n, which is basically this term. So the leading coefficient is 4 here. Here also it is 4. So what do you get? So you get plus 4 into e power minus j pi by 2n plus e power j pi by 2n. Okay, from this term and this term, because this is nothing but e power minus j 6 pi by 4n is same as e power plus j 2 pi by n. This is e power minus j, e power plus j pi by 2n. This is e power minus j pi by 2n. So now that is basically this term. So now what have we cancelled? We have accounted for this and we have accounted for this. What is left out? This e power minus j 3 pi by 4n. What is e power minus j 3 pi by 4n? Is nothing but minus e power j pi by 4n. And this one, 5 into e power minus j 7 pi by 4n is this. E power minus 7 j 7 pi by 4n is e power plus j pi by 4n. And what is the coefficient? 5 and 5, but they are negative. Here it is minus, here it is plus. So what you get? So you get plus 5 minus 5 into e power j pi by 4n again. Okay. And finally, what is left? This middle number. This middle number. Because we have now accounted for this and this. Middle number is 4 into e power minus j 4 pi by 4n. 4 into e power minus j 4 pi by 4n. Okay. So now basically again this is nothing but 4. So again this is 0. This is 0. So this 4 plus 4 into let me make something. So basically while into 2 into e power minus j pi by 2n plus e power plus j pi by 2n whole by 2 plus 4 into um, 4 into what is this 4 into e power minus j pi by n. That's all. Nothing more than that. Okay, so this is nothing but 4 plus 8 into cos pi by 2n. Okay, where is k? Okay, I have missed k everywhere. There should be k everywhere. Okay, there should be k everywhere. K everywhere. Okay. Cos pi by 2 and k plus 4 into. So this is e power minus j pi something but minus 1. So it's minus 1 power n k. X of k is this. Okay, is that okay?
Yes, sir.
Okay. Now let's move to the next question. Compute the endpoint DFT of A x1 of n is equal to delta of n, that is the impulse, discrete impulse. B x2 of n equal to delta of n minus n naught, where n is some number between 0 and capital N. C. x3 of n equal to some alpha power n, where some alpha is some number, where n is between 0 and n. And D. x4 of n equal to u of n minus u of n minus n naught, where again n naught is a number between 0 and capital N. Okay. So let's do one by one. A. So if x1 of n equal to delta of n, basically what happened, therefore your x1 of k, which is your Fourier, discrete Fourier representation, is by definition n equal to 0 to n minus 1, x of n, which is delta of n, into e power minus j 2 pi by n into kn. Now, can anyone tell me what is the summation? What is the summation? So basically what I'm going to use is the shifting property.
Only at the origin.
Correct, correct. You have to use a shifting property of your delta function, of impulse function. That is nothing but delta of 0 into e power minus 2 pi by n into 0 n. Okay, which is nothing but delta of 0, which is equal to 1. Okay, and this is true for all k. Therefore, for all k, your x1 of k is nothing but equal to 1. So if I want to plot, okay, your x1 of k as a function of k, okay, you basically what you will have is the 1 until 0 for k equal to 0, 1, 2, and so on till k minus 1. Okay, so basically DFT is equal to 1 for all k. That is your delta functions DFT. The next question is find the DFT of the signal x2 of n equal to delta of n minus n naught, where, okay, so here the question is where n naught is a number between, sorry, small n naught is a number between 0 and capital N. Okay. Okay, now I think it should be easy to tell, but let's anyways write down the signal. Same logic as you suggested. So if I apply the definition x2 of n, x2 of k equal to summation n equal to 0 to n minus 1 delta of n minus n naught into e power minus j 2 pi by capital N into kn. Yes, now can anyone tell me what is the correct, how to evaluate this sum? Yeah, so again by shifting property, there's nothing but delta of n minus n naught into e power minus j 2 pi by n and k into n replaced by n naught, because you should not sum over all n, because only the delta function takes a non-zero value only when n equal to n naught. So this n should become n naught. Okay, and delta of n minus n naught at n equal to n naught is basically 1. So this is nothing but e power minus j 2 pi by n, sorry, n into k n naught. Or this is also in terms of the twiddle factor w subscript n power n naught k. Okay, for k equal to 0, 1, and so on till k minus 1. Okay, that is the expression for your Fourier DFT. Third question, x3, sorry, I'll just think a different color. So third C, x3 of n equal to alpha power n. Alpha power n. Then basically you compute x3 of k equal to sum over n equal to 0 to capital N minus 1 and alpha power n into e power minus j 2 pi by k into kn. So what I'm going to do is I can write the same as x3 of k summation n equal to 0 to n minus 1 x alpha power n into in terms of twiddle factor wn power nk. This is nothing but summation n equal to 0 to n minus 1 alpha into w power k subscript n whole power n. Now apply geometric series. It is nothing but 1 minus alpha w k w n k power n by 1 minus alpha w n k. Okay, this is basically your DFT for alpha power n. Now the fourth question is when x4 of n equal to un minus un minus n naught, where u is basically a unit step function and n naught is a number between 0 to capital N. So x4, okay, let me write down the signal first. X4 of n is nothing but u of n minus u of n minus n naught. Therefore, your x4 of n k is nothing but summation n equal to 0 to n naught minus 1. That's because from n naught onwards, this u will start to contribute, and that this u of n signal will be killed by u of n minus 1. So only from 0 to n naught minus 1, you are equal to x of 4. X of 4 is basically equal to 1. Basically, this is nothing but 1 if n is between 0 to n naught minus 1 equal to 0. Okay, and then basically what is it in 1 into e power basically, or in terms of total factor w power n k n. That is nothing but 1 minus w n k n naught by 1 minus w n k. Okay, you can simplify this even a little more. For example, okay, take w n k n naught by 2 common in numerator and w n k by 2 common in denominator. So by that, what you can show is that your x4 of k will be basically wn k n naught by 2 into wn minus k n naught by 2 minus wn k n naught by 2 by wn k by 2 into wn minus k by 2 minus wn k by 2. And further, you can show that this is nothing but wn k by 2 into n naught minus 1 by 2. Okay, yeah, k by 2 is anyways there. Into sine n naught pi k by n, capital N, by sine pi k by capital N. I think these kind of relations we have already derived in our previous classes. For k equal to 0, 1, and so on till k minus 1. Okay, so that was about this question, the third question. Now question 4. Find the 10-point DFT of x of k, IDFT, 10-point inverse DFT of x of k equal to 3 if k equal to 0 and 1 if k is between 1 and 9. Okay, so now the way we are going to do about it is, yeah, we'll see if there we can use any property. So we can write this x of k compactly as x of k is nothing but 1 plus 2 into delta of k. Do you agree? So whenever k is equal to 0, this number will become 1. So you have 1 plus 2 equal to 3. For any other k, that is from 1 to 9, what happens is delta k will be equal to 0. So it's just 1. So basically, this x of k function can be represented as 1 plus 2 in delta of k. Okay. So now basically we need to find the inverse Fourier transform of this x of k. Fine. So now we're going to use the properties. So therefore, the corresponding inverse discrete transform is something that IDFT of 1 plus IDFT of 2 into delta of k. Okay, so let's find IDFT of 1. What is IDFT of 1? We saw above. You see here? If I have a delta function, then its corresponding or DFT is equal to 1. Or in other words, if the DFT is 1, the corresponding time domain I inverse DFT is equal to delta of n. Therefore, IDFT of 1 equal to delta of n. From this question, right? This is really this 3a. So now IDFT of 2 into delta of n. Okay. So now, basically, if you recall, by duality property, if one has the delta of n as the DFT, sorry. If delta of n has 1 as the DFT, then what should have something in the time domain so that delta of n becomes a DFT? It's basically applying the duality property. Okay, so let me explain. Let y of n be equal to 1, or here delta of n. Okay. Then we showed that y of k was, what did we show? Equal to 1. That is what we showed. Therefore, your y of n, if equal to 1, will have a DFT as, what will it have? What will it have? 10 n into y of minus n mod n. But delta function is even. So y of n, so basically n into delta of minus n modulo n, which is nothing but n into delta of n. Do you agree? Is it okay? Can anyone confirm if it's okay? If delta of n has DFT equal to 1, then 1 will have the DFT n into delta of k. Sorry, this is not n, this is k. Who should have told me? This is k. Is it okay? Delta of k. Can anyone confirm if it's okay? Yeah, someone confirm. Thank you. The delta of k. That means 1 has DFT n into delta of k, or in other words, 1 by capital N will have the DFT delta of k, or in other words, 2 by n will have the DFT 2 delta of k. Okay? Or what does it mean? It is implies that IDFT, the inverse Fourier transform DFT of 2 delta k is nothing but 2 by n. So put this here. Okay? If you put this here, what do you get? What is n here? N is given to be 10 point inverse. It means n equal to 10. Therefore, this becomes 2 by 10 equal to 1 by 5. Okay? 2 by 10 equal to 1 by 5. Therefore, your solution is x of n equal to 1 delta of n plus 1 by 5. Is it clear? Can anyone confirm if it's clear? Okay. Now we'll do one more
Sir,
question. Hmm.
so how we got 1 by 5?
So here you see 2 by 10. Now we saw that it's 2 by n, right? For this question, n is equal to 10. So 2 by 10 is 1 by 5.
Oh, okay, okay, sir.
Yes. The next question is, we'll take this question and then go for a short break. Find endpoint DFT of x of n equal to 4 plus cos square 2 pi by n by capital N, where n is equal to 0, 1, and so on till n minus 1. Okay, so let's work out the solution. So what are we going to do is, first we will expand our x of n, and then we will use the same trick as we used for discrete Fourier series by using Euler's relation. Okay, so first let's first expand x of n. X of n is nothing but 4 plus cos. Okay, so e power j 2 pi by n by capital N plus e power minus j 2 pi by 2 pi n by capital N by 2 the whole square, which is nothing but 4 plus 1 by 4 into e power j 4 pi by n plus e power minus j 4, okay, small n, 4 pi n by capital N plus 2 into e power plus j 2 pi by n by n into e power minus j 2 pi n by n, both will cancel, so it's just 2. And so there's nothing but 1 by 4 into e power uh, minus j 4 pi by n into n plus 4 plus half. 1 by 4, 1 by 4 into 2 is basically half, plus this 4 is the right, so it becomes 9 by 2 plus 9 by 2 plus 1 by 4 e power j 4 pi n by n. But now see, this I can write it as, this is same as e power j 4 pi by n minus n by n. Is it okay? That's because you can write this as e power j 4 pi n by capital N into e power minus j 4 pi. E power minus j 4 pi is nothing but uh, okay, so maybe the other way to do is not this way. Okay, we will take this. We will take concentrate on this. Okay, so this is nothing but e power minus j 4 pi by n into n is same as e power minus j 4 pi by capital N into e power minus plus j 4 pi, which is nothing but e power plus j 4 um, 4 pi. Okay, 2 pi by okay, maybe I'll just take 2 pi. Why 4 pi? Just take 2 pi e power j 2 pi by capital N into n minus 2n. Is it okay? I just rewrote. So e power minus j 4 pi by n into n is same as e power plus j 2 pi by n into n minus 2 into n. Okay. Then what am I having? Let me rearrange this equation. So we have equal to 9 by 2 plus 1 by 4 into e power j 2 pi by n into 2n plus 1 by 4 into e power j 2 pi by n into n minus 2n. Okay, call this is nothing but our x of n. Call this is equation 1. But now also recall from your definition of your inverse Fourier transform 1 by n into summation k equal to 0 to n minus 1 x of k into e power j 2 pi by n into kn. This is equation 2. Now compare 1 and 2. If you compare 1 and 2, what do we have? Can I say that for k equal to 0, your 1 by n should be equal to, sorry, x of k into 1 by n should be equal to 9 by 2, which implies your x of k equal to 9 by 2n. I'm just comparing term by term. There are n terms here. There are 3 terms here. That means only 3 of the k's will be having non-zero values. For every other k, it will be 0 value. For especially for k equal to 0, this term will equal to 1. This is x of 0, 1 by n. That should match the first term because it doesn't have any e power exponential term. That means 9 by 2 should equal x of k by n for k equal to 0. That is x of 0 by n into equal to n by 2, 9 by 2. Therefore, x of 0 or x of k for k equal to 0 is equal to 9 by 2 into n. Now, what is the next complex exponential present? So, if you remember 2 pi by n, here it is there, here also it is there. What is difference is 2n versus k. And that means for k equal to 2, for k equal to 2, your x of k by n should equal to, what should it be equal to? Yes, I'm just comparing for k equal to 2k's. I'm comparing between equation 1 and equation 2. For k equal to 2, here the coefficient is x of k by n, which is equal to this. What is the coefficient of k equal to 2 term here? 1 by 4. Equal to 1 by 4, which implies your x of k equal to n by 4. Similarly, for k equal to, what is the other k left out in the equation 1? N minus 2. For k equal to capital N minus 2, your x of k by n is again equal to 1 by 4. It implies your x of k is again n by 4. For any other k, what is your x of k? Your x of
Zero.
k, correct, equal to 0. Implies your x of k equal to 0. Therefore, what is the question? Find the DFT, that is x of k. We have found the x of k now. Therefore, summarizing, your x of k is equal to 9n by 2 if k equal to 0, n by 4 if k equal to 2 or k equal to n minus 2, and 0 if otherwise. Okay. Okay. So now it's 7:15. Let's take break till 7:25 and then let's come back. Okay, so let's resume. Am I audible and are you able to hear me?
Yes, sir.
Okay, thanks. Okay, so next question is, consider the finite length sequence x of n equal to delta of n plus 2 into delta of n minus 5. Okay, so the question is, A, find 10-point DFT of x of n. B, find the sequence that has a DFT y of k equal to e power j 2 pi into 2 pi by 10 into 2k into x of k. Okay, so it's a very simple question. So first one is again straightforward. So what is the, I think now by now you should be able to tell me. So basically what is the DFT of x of n is nothing but delta of n plus 2 into delta of n minus 5. So if I apply the definition of x of k, it's nothing but summation n equal to 0 to n minus 1 x of n into e power minus j 2 pi by k into kn. And that's nothing but summation n equal to 0 to n minus 1, split the summation delta of n into e power minus j 2 pi by k into kn plus summation n equal to 0 to n minus 1 to take it outside summation delta of n minus 5 into e power minus j 2 pi by k into kn. Okay, so the first term, if you see what is the first term, delta function has non-zero only when n equal to 0. Therefore, it becomes 1.
1.
Correct. What is the second term?
2
Yes.
into 2
Hmm.
into e to the power minus j 2
Hmm.
pi divided by k.
Hmm.
Is
Sorry, n,
equal
not
to
k.
5.
Hmm.
Sorry.
Sorry, n,
Right. K 5.
k 5. Correct. Absolutely. 5k. Okay, that's absolutely correct. But now, okay, so here n is what? 10 because it's given 10-point DFT. Therefore, there's nothing but 1 plus 2 into e power minus j. 2 pi by 10 is nothing but pi by 5 into 5k, which is equal to 1 plus 2 into e power minus j pi k, which is nothing but 1 plus 2 into minus 1 power k. Is it okay?
Yes, sir.
Yes. Now, what is the next question? Now, let's say that now I construct another sequence y of n whose Fourier transform y of k is equal to e power j 2 pi by 10 into 2k into x of k. That means by time shifting property, what is y of n? X of n plus 2. Do you agree? Why n plus 2? See, n minus n naught will give rise to e power minus j 2 pi by k into k n naught times your x of k in frequency domain. But here, if you look at it, n here it is plus, which means your n naught is equal to minus 2. Therefore, n minus n naught will become n plus 2. That's why I wrote n plus 2. Is it okay? So basically, your y of n is nothing but x of n plus 2 itself. But what is x of n? Delta of n. Um, but okay. Let's do one thing. Okay. N plus 2. But of course, you need to take modulo 10, right? So modulo 10. Therefore, this is nothing but delta of n plus 2 mod 10 plus 2 into, sorry, delta of n minus Okay, minus 2 minus 5, right? Minus 2 minus 5, sorry, plus 2, yeah, plus 2 mod 10. So that is nothing but so this happens, this basically n plus 2 mod 10 is nothing but, can I write this as delta of n minus 8? Can I write this as like this? Because this delta function has a non-zero value only at n equal to minus 2. But I'm interested in n equal to 0, 1, and so on till capital 10, 9. Okay, it should have been one among these. Therefore, minus 2 mod 10 is same as 8 mod 10. Therefore, I do delta of n minus 8. Similarly, the other thing will be 2 into delta of n minus 3. This is fine, no problem, because when the moment I add 2, it will become minus 3, which is lying between 0 and 10. So it's just delta of n minus 3. Is it okay? Because I'm supposed to represent between 0 to 9. But here, n plus 2 would have given a non-zero value in n equal to minus 2. That is not the range in which I'm looking for. So I shifted by one more period. Is it okay? I didn't. Sorry, did you, is it okay? Did you follow?
Yes, sir. Yes.
All right. That was question 6. Okay, that finishes question 6. Now let's do question 7. Okay, very similar question only. So we are going to use properties of Fourier transforms. Let x of n be equal to 4 delta of n plus 3 delta of n minus 1 plus 2 delta of n minus 2 plus delta of n minus 3. Okay. Then given, let x of k be the 6-point DFT of x of n. Okay, I'm taking 6-point DFT of x of n. The first question is, find the finite length sequence y of n that has a 6-point DFT y of k equal to e power minus j 2 pi by 6 into 4k into x of k. That is question 1. Question 2, find the finite length sequence w of n that has a 6-point DFT equal to real part of x of k. That is w of k equal to real part of x of k. Do you understand? So what I'm saying is, I have given you an already signal x of n and its corresponding Fourier transform 6-point DFT is x of k. Now let me construct another Fourier transform y of k is equal to this e power j 2 pi by 6 4k into x of k, and I'm asking what is the corresponding time domain signal for y of k. Next, our next question, this x of k, whichever I obtain from x of n, you take the real part of the x of k for every k, and then tell me what is the equivalent time domain signal whose DFT is a real part of this x of k. These are the two questions that we need to solve. Let's do one by one. Okay, let's do one by one. So what is, okay, so you see, if you look at this is nothing but immediate, that you have to apply what? Time shifting property of the Fourier transform. Now, by what has it shifted? Minus 4. So n naught equal to 4 is the shifted property. So A, by time shifting property, what should you do? Your y of n is nothing but x of n minus n naught modulo, what is it? 6, because n is equal to 6 here, modulo 6. What is n naught here? N naught is nothing but 2. Sorry, not 2, 4. Correct? Therefore, this is nothing but x of n minus 4 mod 6. That is nothing but, what is the first term in x of n? 4 delta of n. So that will remain 4 delta of n minus 4 mod 6 plus, next term is what? 3 into delta of n minus 1. 3 into delta of n minus 1 minus 4 mod 6 plus 2 into delta of n minus 2. 2 into delta of n minus 2 minus 6 mod 6 plus last is what? Delta of n minus 3. Delta of n minus 3 minus 6 mod 6. This is nothing but 4 into delta of n minus 4 plus 3 into delta of n minus 5 plus 2 into delta of n plus delta of n minus 1. Why did I do that? Because this is nothing, this is nothing but delta of n minus 6 mod 6. That means I'm already shifting by 6 units. And then if I take a modulo 6 again, this is same as delta of n. Similarly, this is nothing but delta of n minus 9 mod 6. So I'm shifting by 9 units. And I'm taking the remainder when I divide by 6. So this is same as delta of n minus 3. Yeah, it's n, sorry. Is it correct? Delta of n minus 3 minus 4. Why did I write 6?
Yes.
It's not 6, this is 4. So 4 minus 2 is nothing but n minus 6 mod 6 is nothing but delta of n. And n minus 7. N minus 7 mod 6 same as delta of n minus 1. Is it okay? So,
Yes, yes, sir.
so this is basically your y of n. Now, second question. What is the second question? Find the sequence W of n whose Fourier transform W of k is nothing but real part of x of k, where x of k is the DFT of this number, 6-point DFT, this sequence. So let's solve this interesting question. So what is real part of x of k? It's nothing but x of k plus x of k conjugate by 2. Correct? Therefore, your W of n must be IDFT of x of k plus IDFT of x conjugate of k by 2, which is nothing but IDFT of x of k is nothing but x of n by 2 plus IDFT of x conjugate of k by 2. Okay, so what remains is we need to compute the IDFT of x conjugate of k. Let's do that. IDFT of x conjugate of k. So recall that basically what is your x of k is nothing but, just writing the definition of DFT, summation n equal to 0 to n minus 1 x of n into e power minus j 2 pi by k into k n naught n. What this implies that x conjugate of k is equal to, take conjugate on both sides, summation x of n over n e power minus j 2 pi by k k n whole conjugate. That is same as summation over n x conjugate of n into e power j 2 pi by capital K, sorry, capital N, not K, so capital N into Kn. But This one I can again write it as equal to summation n x conjugate of n into e power j 2 pi by n into kn into e power minus j 2 pi. Okay. Then what I can write is write this as summation over n x conjugate of n into e power minus j 2 pi by n into n minus nk. Do you follow till this step?
So why you have taken e to the power minus j 2 pi? Means how you exactly you
That's,
brought that?
that's because equal to this is equal to 1, right? Anyways, I'm multiplying by 1 and just I'm writing 1 as e power minus j 2 pi. That's all. What is e power?
Okay.
I'm just e power minus j 2 pi is nothing but cos 2 pi minus j sine 2 pi. This is anyways equal to 0. This is equal to 1. So I'm just multiplying by e power minus j 2 pi will not change the answer because anyways it is equal to 1 only.
Okay, got it.
Yeah. From this step to this step, is it okay? I just clapped both of these into single exponential.
Yes, sir. This understood.
Yeah. Now what is it? Now I will tell you something. Put n dash, define another number n dash as n minus n mod n. Okay. So you can show that if you with this variable substitution, change of variables, this above summation will become n dash equal to 0 to n minus 1, x conjugate of n minus n, sorry, n minus n dash mod n into e power minus j 2 pi by n into n dash k. Okay. You can show that this you can do. Why did I remove mod k from here? That's because anyways n ranges from n to 0 to n minus 1. So n minus n will again range from 0 to n minus 1. So mod n, nothing will happen. It will be the same number. Because anyways it's a number between 0 to n minus 1. So it will not this, there is no mod thing happening. Okay, so this is now what is this? What is this? DFT of x conjugate of n minus n mod n. Is it clear? See, if I want to compute DFT of this, what do? You summation over this into e power minus j 2 pi by capital N and k. That is exactly this, right? Just that n dash is now n dash is same as treated as n. Okay, so this is nothing but DFT of x conjugate of n minus n mod n. But what is this? X of k. Therefore, what is IDFT of x conjugate of k? Therefore, IDFT of x conjugate of k is equal to what is it? X conjugate of n minus n mod n. That's all. This is equation 2. Call this as equation 1. Put 2 in 1. What do you get? W of n is nothing but x of n by 2 plus x conjugate of n minus n mod n by 2. Okay. So now what we need to compute is what is x conjugate of n minus n mod n. Okay. Here what is n? Capital N is nothing but it's given to be 6 point. We also know what is x of n. 4 delta of n, 3 delta of n minus 1, 2 delta n minus 2 plus delta n minus 3. Okay. So that is basically what is the x of n? Recall your x of n is nothing but 4, 3, 2, 1, where 4 is at n equal to 0. Therefore, if I do, okay, let me call this y of n is nothing but x conjugate of n minus n mod n. Therefore, y of 0 is nothing but x conjugate of n is nothing but 6 here, right? 6 mod 6, which is equal to x conjugate of 0, which is equal to 4. Y of 1 is nothing but x conjugate of 6 minus 1, which is 5 mod 6, which is equal to x conjugate of 5. What is x conjugate of 5 here? Which means I'm essentially assuming 0, comma 0. It's a 6 point, right? So I need to append the 2 more zeros. So x conjugate of 5 is 0. Y of 2 equal to x conjugate of 6 minus 2, which is 4 mod 6, which is nothing but x conjugate of 4, which is again 0. Y of 3 equal to x conjugate of 6 minus 3, which is 3 mod 6, which is nothing but x conjugate of 3, which is nothing but 1. Y of 4 is nothing but x conjugate of 6 minus 4, which is 2 mod 6, is nothing but x conjugate of 2, which is nothing but 2. And finally, y of 5 is nothing but x conjugate of 6 minus 5, which is 1 mod 6, which is x conjugate of 1, which is nothing but 3. Okay, therefore, your x conjugate of n minus n mod n is nothing but 4, 0, 0, 1, 2, 3, where 4 is at n equal to 0. Okay, therefore, what is W of n? Therefore, what is your W of n? Half of 4, 3, 2, 1, 0, 0. 4, 3, 2, 1, 0, 0 plus 4, 0, 0, 1, 2, 3. What is this? 4 plus 4 by 2 is nothing but 4. 3 plus 0 by 2 is nothing but 3 by 2. Then 2 plus 0 by 2 is nothing but 1. Then you have 1 plus 1 by 2 is nothing but again 1. 0 plus 2 by 2 is nothing but again 1. And 0 plus 3 by 2 is nothing but 3 by 2. With 0 equal to 4. Is it clear? Can you confirm if it's clear? Hello, am I audible?
Yes, sir. Yes, sir. It's clear, sir.
Is the solution clear?
Yes, sir.
Okay. Next to question 8 now. Let the Fourier transform, let these 8-point sequence x of n have DFT x of k equal to k plus 1. Okay, that is k ranging from 0 to 7. Okay, so I'm giving you the DFT already. Now the question is, find summation n equal to 0 to 3 x of 2n. Okay, it's a very interesting question, but actually this question comes by some observation, very careful observation. So now, basically, what is this? What are we asking? Essentially, we're asking what is x of 0 plus x of 2 plus x of 4 plus x of 6. Correct? We are asking what is the sum of these two samples, these 4 samples. If your DFT of the samples x of n is k plus 1 for k between 0 to 7. So a very crucial observation is as follows. What is x of k? That is your discrete Fourier transform is given by x of k equal to summation n equal to 0 to n minus 1 x of n into W8 Kn. Is it okay? This is the definition of discrete Fourier transform. Therefore, what is the x of 0? Capital X of 0 is nothing but put n equal to 0 in the above equation. Sorry, k equal to 0 in the above equation. N equal to 0, n minus 1, x of n into w power 0, 8, which is equal to summation over xn. Because w8 is in turn e power something, but e power 0 is something but 1. So it's just summation over n. N equal to 0 to n minus 1. Now I'm going to consider x of 4. The frequency DFT of the fifth sample, fifth frequency sample, that is equal to x of 4 is nothing but summation over n equal to 0 to n minus 1 x of n into w8 power 4n. Okay, but now what is w8 4n? It's nothing but e power minus j 2 pi by 8 into 4n, which is nothing but e power minus j pi n, which is nothing but minus 1 power n. Correct? Therefore, the above equation becomes summation n equal to 0 to n minus 1 minus 1 power x. Okay. Now, can you make out something? What should I do? So I have x of 0 is equal to sum of xn. X of 4 is equal to sum of minus 1 power xn. And I want to find sum of x0, x2, x4, x6. Can you tell me what to do with these two equations? Okay, if you want me to be elaborate, let me write down what x of 0 is. X of 0 is nothing but x of 1, 0 plus x of 1 plus x of 2 and so on till x of 6 plus x of 7. And x of 4 is nothing but minus 1 power n into x of n. So it is nothing but x of 0 minus x of 1 plus x of 2 minus x of 3 and so on till plus x of 6 minus x of 7. Okay, now can you tell me how to obtain x of 0 plus x of 2 plus x of 4 plus x of 6? Yes. Simple, right? Just add both equations. If I add both equations, what do I get? X of 0 plus x of 4. All these even odd terms will get knocked off. Correct? But what will remain is what? 2 into x of 0 plus x of 2 plus x of 4 plus x of 6. Or in other words, x of 0 plus x of 2 plus x of 4 plus x of 6 is nothing but capital X of 0 plus capital X of 4 by 2. But we know this. Why? Because it's given that x of k is equal to k plus 1. Therefore, x of 0 is nothing but 0 plus 1, 1, and x of 4 equal to 5. Therefore, this is nothing but 1 plus 5 by 2, which is equal to 3. This is nothing but summation over n equal to 0 to 3 x of 2. Is it clear?
Yes, sir, got the point.
Yeah. It's just merely by observing the definitions of your Fourier transforms. Okay, so let's solve one last question for today and then we'll close for today. The question is, let x of n be given as delta of n plus 2 delta of n minus 2 plus delta of n minus 3. Okay, simple. First question is, find 4-point DFT of x of n, and B, if y of n is a 4-point circular convolution of x of n with itself, then find y of n and 4-point DFT y of k. Okay, this is the last question for today. So the first question is again simple, right? So what is your x of n is nothing but delta of n plus 2 delta of n minus 2 plus delta of n minus 3. So you can just apply the Fourier transform definition, right? So you can show that this comes out to be 1 plus 2 into W4 2k plus 1 into W4 3k. That's all. This is the DFT. Where W is a twiddle factor. Now, second question, what it says is your y of n is a circular convolution of x of n with itself. That is again circular convolution. That means, what does it mean? Your y of k is nothing but x of k into x of k by convolution property. Okay, that means it's nothing but 1 plus 2 W4 2k plus W4 3k the whole square. You can show that you can just work it out. You can show that this will come out to be 5 plus 4 W4k plus 5 W4 2k plus 2 W4 3k. Okay. Or now tell me what is y of n? What is the inverse DFT of y of this expression y of k? 5 delta of n.
5 delta
Yes. Yeah.
n
Plus.
plus 4 delta n minus 1
Correct.
plus 5 delta n minus 2
Correct.
and plus 2 delta n minus 3.
That's it. Okay. So only step is you verify this. Just verify. Just expand a plus b plus c the whole square and then use the properties of the twiddle the e power j 2 pi by n into nk. Use the periodicity of exponential function and then show that it will turn out to be this.
Okay,
Okay.
sir. I'll.
So that basically finishes this question and also the final question for today. So are there any questions, any doubts in DFT that we have discussed today?
No, sir.
Okay, great. So then we will stop now. We will continue our discussions. Oops. Where is it?
Okay. Okay.
Just a,
Thank you, sir.
yeah.
Okay.
Okay.
Okay, sir.
Yeah. Thank you.
Thank you, sir.
Hmm.